In this video, we're going to look at using the quotient rule using tables, graphs, and then also relating quotient rule to our tangent and normal lines. So in this first example here, we're going to look at using the quotient rule to find the derivative when we're given information in a table format. So here they're telling me that when x is 6, that f of 6 is 5, g of 6 is 8, f prime of 6 is 3, and g prime of 6 is 6. And they're defining h of x as this quotient of f of x divided by g of x. So again, I kind of went off to the side and I set up my pieces for my quotient rule. So again, I'm letting f represent the function on top and g represent the function on the bottom of my fraction. And then I found the derivative of those pieces. And then over here, I just built my quotient rule using low d high minus high d low all over the square of what's below there. So in this problem, our goal is to find h prime of 6. So what I want to do now that I've expanded this out in function form is I want to replace all of those x's with 6 into that quotient rule. So now instead of g of x, we're going to have g of 6. Instead of f prime of x, we're going to get f prime of 6, f of 6, g prime of 6, and then at the bottom, we're going to find g of 6 and square it. Now, in this case right here, since we didn't know what f of x and g of x were as functions, we have to rely on the table to grab these values. So g of 6 is going to be 8. F prime of 6 is going to be 3. F of 6 is going to be 5. And then g prime of 6 is going to be 6. And then I'm going to put that all over g of 6 squared, which is again 8 squared. Once I replace all of those with their numbers, now I'm just going to do my regular math. So 24 minus 30 up in the numerator, 64 down in my denominator. And when I clean this up, I get negative 6 divided by 64. And then I can reduce that and say that h prime of 6 is negative 3 over 32. So when we're using the quotient rule, just pay attention to who's in the numerator and who's in the denominator. We're always going to define f as the numerator, g as our denominator, then we're going to find our derivatives of each piece and then follow our quotient rule for that. In this case, all of our values came from a table, but we could do a similar type of problem where we're given a function, and instead of being given our information about function values and derivative values in a table format, we might need to use a graph to grab that. So here they're telling me that k of x is found by doing f of x over g of x. So similar to my last example, f is my numerator, f of x, g is my denominator, g of x. I found my derivative f prime and g prime. And then over here, I went ahead and I built my quotient rule for this function. So it's the same exact expanded form as our last example, but now we're calling it k instead of h. So this is k prime of x. In each of these problems, they're telling you to replace the x with different values. So we're going to go in here, and in this first round, we're going to replace all of those x's with 1. And then we're going to interpret the information from the graph to get our function and our derivative values. So for k prime of 1, what we want to do is replace all of these x's with 1. So we're going to have g of 1 times f prime of 1 minus f of 1 times g prime of 1. Oops, that's too many parentheses there. All over g of 1 squared. Now when I'm using a graph and they want me to find g of 1 or f of 1, I'm just going to go to where the x value is 1 and find my y coordinates. And f of x is this upside down v graph, g of x is this line. So g of 1, when I jump on my g graph where x is 1, that's this point right here, that's going to be 3. And when they're asking us to find our derivatives at that point, we're going to go to the function, and the derivative at 1 is going to be the slope of the line that's passing through 1. So when I look at this right here, on this graph, all of my slopes are up to over 1. So at any point from 0 to 2 on f of x, its derivative is going to be 2. So f prime of 1, because it's on this piece, f prime of 1 is 2. And then f of 1 happens to also be 2 because when x is 1, I hit that point right there at 2. G prime of 1, however, when I go to 1, G prime of 1 is going to be the slope of this downward segment. So any point on this function for G, if I look at the slope, it's going down 1 over 1, down 1 over 1. Anybody on this one has a slope of -1. So when x is 1, G prime of 1 is going to be that slope of -1. And then G of 1 squared, again, when I'm at 1, G had a value of 3, so my denominator here is going to be 3 squared. So all I have to do to finish up this problem now is just do the math. So if I work this out in the numerator here, I'm going to get 6 plus 2, which is 8. Then down here, 3 squared is 9, and I can't reduce that, so that's going to stay 8/9. We basically repeat the same thing for k prime of 3, but now we're going to look at what happens when x is 3. And when x is 3, I'm going to find g of x by looking at where this line is hitting there at y. For f of x, I'm going to grab this point, and then again, their primes, their derivatives, are going to be the slopes. So the only thing that's focusing now and changing is that right here, when I'm between 2 and 4, my slope is now decreasing, and it's going down 2 over 1. So if I'm going through here, I'm going to replace all of these x's with 3. I'm just going to go grab my values and put them into my function here. So g of 3, when x is 3, g with 3 is 1, so I'm going to use 1. F prime of 3, when x is 3, I'm at this point right here. My slope is -2. F of 3, when x is 3, my y coordinate is +2. And then g prime of 3, again, anybody on the g of x had that slope of -1. All over g of 3 squared. So again, when x is 3, g of x was 1, so that's going to go all over 1 squared. So I'm going to get -2 plus 2, so I'm going to get 0 over 1, and that'll simplify to just 0. Now, the one thing we want to keep in mind is, again, whenever our graph has a sharp corner, we know the derivative doesn't exist at that value. So in this case right here, because the graph abruptly changed from a positive slope of 2 to a negative slope of -2, there was an abrupt change. That means that my derivative does not exist at that point. So in this case, f prime of 2 does not exist. And if f prime of 2 does not exist, then that means that any function that's involving f of x at 2 does not exist. So right away, without doing any work, I know that this is not going to exist because f prime of 2 does not exist. And I know when I'm building this function, I'm going to need f prime of 2. So when we're using our quotient rule, again, just pay attention to our functions because sometimes they might define the numerator as g and they might define the denominator as f. So always think about how this is relating back to the location of those original functions. So that little rhyme will help you out. So it's low d high minus high d low all over the square of what's below. And if my low function is f of x, then I would actually start with f of x here. Now, sometimes we might see a function that starts out looking like a good candidate for our quotient rule because we can see clearly that this guy is a fraction. But I don't always have to use quotient rule with fractions. If I have a fraction and in my denominator is a single term, I can go ahead and rewrite my function by taking each piece in the numerator and dividing it by that denominator. I'm basically uncombining fractions there. So when they added together to have that common denominator of x, I really had that first term over x plus that second term over x. And then what I can do is keep simplifying here. If I have radicals, I want to rewrite them as rational exponents. So instead of the square root of x, I can take the inside power divided by the root. And then I can further simplify f of x now by using my properties of exponents to simplify each term. In this case here, I would keep my base x and subtract my exponents. So this would reduce down to 3x. And then here, I would keep my base x, subtract my exponents. 1/2 minus 1 would give me a negative 1/2. So even though this started out life as a fraction, instead of using quotient rule, I can just use properties from algebra to separate the numerator into individual fractions over that common denominator, and then apply some properties of exponents to simplify. And now, this is the new look for f of x. So now I can just apply my power rule and find my derivative. And this is going to be a lot quicker and easier to do than trying to do the quotient rule. So the derivative of 3x would just be 3. And in this case, I would multiply 2 times negative 1/2 to get negative 1x. And when I subtract 1 from that, it's going to go lower. Negative 1/2 minus 1 would give me a negative 3/2. And I would leave my answer just like that. I don't have to rewrite that back in radical format, and I don't need to rewrite this as a positive exponent in the denominator. I would just leave my answer like that. For our final example, what we're going to look at is one more quotient rule example, but using our tangent and our normal lines, just to kind of review those concepts that we looked at before. And when we're working out this problem, they're defining my function y as this fraction. I can't use my little separation technique because the denominator has more than one term. So separating this isn't going to be helpful. So again, when I have a fraction that I can't simplify, one thing I can do is rewrite that numerator as x to the 1/2. And then I can go ahead and identify the parts for my quotient rule. So again, for the quotient rule, I'm going to define f as the top piece. And I'm going to use it in that exponent form. I'm going to define g as the bottom piece of that fraction. I'm going to find f prime by taking the derivative, applying the power rule. And I'm going to find g prime by using my power rule here. When I go to find the slope of my tangent line, remember the slope of our tangent line is the value of the derivative at that point. So to find my derivative, I'm going to use, again, my quotient rule. So I'm going to do low d high, so the 1 plus x squared times the derivative of that f, so 1/2 x to the negative 1/2, minus, and then high d low, so x to the 1/2, times that derivative of g, all over the square of what was originally there. If I want to write the equation of the tangent line at the point 1/2, what I'm going to do is let x equal 1 and find my slope of my tangent line when x equals 1. Which means I'm going to go in and I'm going to replace all of my x's with 1. And I'm not going to bother trying to simplify this because I can just do the math in pieces here. So if I replace the x's with 1, I'm going to get 1 plus 1 squared, or 1, times 1/2 times 1 to the negative 1/2, or just 1/2 times 1, minus 1 to the 1/2, or just 1, and then 2 times 1, which is 2. 1 plus 1 squared is 1 plus 1 squared. And then I'm just going to do the math. So 1 plus 1 is 2. 2 times 1/2 is 1. 1 times 2 is 2. So I get 1 minus 2 over 4. That's going to give me negative 1/4. And that's my slope of my tangent line. And with that tangent line slope and that point, now I can write my equation of my line. And again, once we know our tangent line slope, at that same point, the normal line slope is just the opposite reciprocal. So if my tangent line slope was negative 1/4, my normal line slope is 4, and I'm going to use this point, this slope with that same original point. So I'm going to do y minus 1/2 equals 4, and then parentheses x minus 1. And that's my equation of my tangent line. And that's my equation of my normal line. And they look exactly the same, except the slopes are opposite reciprocals. That's my tangent slope. There's my opposite reciprocal for my perpendicular slope for my normal line. At this point now, you should be able to go back to those book problems that were assigned yesterday and finish up any of the ones that you had trouble with.